Welcome back. In this video, we'll consider the function of a complex variable and proceed to provide some very key definitions to some kinds of functions that we have. Now, earlier we have already looked at the concept of functions in the terms of its continuity as well as the differentiability of those kinds of functions. But this time around, we want to talk about some very important kind of functions, of complex functions that we have. As always, make sure to like, share, and subscribe, and turn on your notifications so that you do not miss any of our videos. Now, remember, we have defined the function of a complex variable as w equals f of z. And we said, of course, where z is a complex number, which, of course, can be written as z is equal to x plus iy. Now, the moment you consider the complex number in terms of its real part, and of course in terms of its imaginary part, then in that regard, it means that you could define the function of a complex variable as a function of two real variables, because x and y are of course real numbers. Now, this function of a complex variable can also be written with a real part of the function and as well an imaginary part of the function, hence written u and v. So this is very important to keep in mind. Now, a good example of a function like this is a simple function. If we refer to a function like f of z, which is equal to z, this is a very simple and basic function, which you can of course rewrite as x plus iy, which would mean that in this case you are saying that u is equal to x and then v is equal to y. This is the simplest you can find as far as the complex function. Now, there is a very important kind of complex function that we usually use when it comes to complex analysis, and that is where we refer to the analytic function. Now, the analytic function is a very important kind of function that we have as far as complex analysis is concerned. And the necessary and sufficient condition for analyticity will be stated now. Now, we say that a function, a complex function, f of z is indeed analytic if 1, the first 4 partial derivatives are continuous, and then 2, it satisfies what we refer to as the Cauchy-Riemann equation, CRE for short. Now, this is the necessary and sufficient condition for a complex function to be analytic. When you take the first condition, which is the first 4 partial derivatives being continuous, that is the sufficient condition. And then when you say it satisfies the Cauchy-Riemann equation, that is the necessary condition, which means if the first 4 partial derivatives were not continuous, then it would mean that not all those partial derivatives will exist. And if not all of them exist, then you would have enough of the parameters that you would need to throw into the Cauchy-Riemann equation for you to see if it satisfies or not. Now, the very first thing is, what exactly is the Cauchy-Riemann equation? We say for a fact that when we talk about the Cauchy-Riemann equation, it is simply referred to as the relationship between the first 4 partial derivatives of a complex function, right? For the Cauchy-Riemann equation, there are 2 broad definitions or 2 broad equations when the function is indeed an algebraic function. We say that in this regard, if ux, which is the partial derivative of u with respect to x, equals Vy and Vx, which is the partial derivative of v with respect to x, equals minus uy. If these two equations are satisfied, then you say you have satisfied the Cauchy-Riemann equation. These are the two Cauchy-Riemann equations you have. If you want to write them in full, you can write them as del u del x equals del v del y, and del v del x equals minus del u del y. These are the Cauchy-Riemann equations. Of course, remember that I have said that this specifically discusses when you have algebraic forms of the complex function, which is forms when you can easily identify x and y, right? You could also have a variation of the Cauchy-Riemann equation in terms of the polar form, right? Which of course can be easily generated still from its algebraic form. We'll look at that very, very shortly. But first, let's recount what we have. We have that the analytic function exists if the first four partial derivatives are continuous, which is you are saying ux, uy, because you have two parts of the function, the real part and the imaginary part. You are saying ux exists, uy exists, vx exists, and then vy exists. Those are the first four partial derivatives. And then those parts are continuous, and you now show that they satisfy the Cauchy-Riemann equation, which means when you equate them in this order, they give you exact equality, right? So once these two are satisfied, these are the necessary and sufficient conditions. Once these two are satisfied, then you see the function is indeed an analytic function, right? Let's take a very, very simple example to see what exactly this means. For instance, if we are to show that e raised to power z is an analytic function, of course, if we let w equal e raised to the power of z, right? Of course, w is the complex function. We can write that as u plus iv, right? Since z is of course equal to x plus iy, right? Then it means that we can rewrite w as e raised to the power of x plus iy. Now, by the laws of indices, we can write this as e raised to the power of x multiplied by e raised to the power of iy, right? But by the relationship between the exponential form and the polar form, we know that if I have e raised to the power of iy, it's as if I already have myself another complex number inside, which can then be written as cos y plus I sine y, right? Because we know that e raised to the power I theta equals cos theta plus I sine theta. Good. Which means that I can expand w as e raised to the power of x cos y plus I raised to the power of x sine y. So I have myself my u, and then I have myself my v, right? So first off, let's see if the first four partial derivatives exist. Now, u equals e raised to the power of x cos y. So if I differentiate this partially with respect to x, that will mean cos y will become a constant, or it will be the coefficient in this case. And so my differential of e raised to the power x remains e raised to the power x. So I'm still going to have e raised to the power x cos y. Similarly, if I differentiate partially with respect to y, the e raised to the power x takes my constant position, which means it should be the coefficient here. Differential of cos y will give me minus sine y. So I'm going to have minus e raised to the power x sine y, partial derivatives. Similarly, if I go for v, which is equal to e raised to the power x sine y, then this would simply also be, meaning that v of x, which is partial derivative of v with respect to x, this time around sine y would be my constant coefficient. This would be e raised to the power x sine y still, and then Vy, which is partial derivative of V with respect to y, this by x would be my constant coefficient. This should be e raised to the power of x cos y, because the differential of sine y gives me cos y. So my differentials, I could find my differentials, right? And remember, if the function is differentiable, then it means that function is continuous. So I could find my first four partial derivatives, which means they will definitely be continuous, right? So first condition checked. Now, do they satisfy the Cauchy-Riemann? Is ux equal to vy? Look at the right hand side. It's the same. So since ux is equal to vy, what about the other condition? Is Vx equal to minus Uy? Yes, because if you take this, Uy in this regard is minus Vx. So we are good. So you can say that Uy is equal to minus Vx. So since these two conditions are satisfied, which is the Cauchy-Riemann, so you can see that then the CRE is indeed satisfied and e raised to the power of z is indeed analytic. And here we have it. So we have shown that indeed the function would be analytic if you can find the first four partial derivatives, which will mean that they are continuous. And then we can verify that the Cauchy-Riemann equation is indeed satisfied. So this is how to proceed to solve when it comes to verifying the Cauchy-Riemann equation, as well as verifying that a function is indeed analytic. As always, if you have any questions, you can drop them in the comments. And if you want more clarity on how we carried out the partial derivatives, and if you probably would want to request a video on that, also let us know in the comments. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.